All right, so welcome everyone to the latest IQS presentation. We are delighted to have David Arvidsson Shukur visiting here from Cambridge in the UK. He has been doing a tour of the US of a lot of various places, and we're lucky he stayed here for a couple weeks to talk some interesting physics. He's been doing a lot of work with the Hitachi lab, who is funding his visit here, I believe. And he'll tell us all about the details of weak value amplification and weak values that even we don't know here at Chapman, which is pretty impressive. So I'm looking forward to hearing what you have to say. Thank you, David.
Thanks a lot, Justin. And it's really been a pleasure. Chapman has been my kind of favorite spot during this kind of US tour, not only because of the great people, but also because you have such a wonderful campus. It must be super nice to work and live in an environment like this. Okay, so let's get started here. I don't know if it's stuff that you guys don't know. We'll see about that. But so I think Andrew coined the terminology or the phrase two-state vector formalism on steroids during this conference we just attended. And maybe this is a bit of an attempt towards weak value amplification on steroids. So what am I going to talk about? I'm going to talk about metrological quantum information, so information about unknown things, and how much can you compress this information into quantum particles. So this is what I'm going to talk about. Before that, as you mentioned, Justin, I come from this Hitachi Cambridge laboratory in Cambridge. I just thought I'd mention a few words because not everyone knows what it is. Not everyone should know what it is, but it's a privately funded lab which is embedded within the Department of Physics at the University of Cambridge. It's funded by Hitachi Ltd, the huge Japanese technology company. And they pay my salary, and they've been funding this visit for me. And they've had a private lab in Cambridge since the 1980s, so for over 30 years. And for a long period of time, they were working on developing kind of solid-state hard drives and stuff like this for classical computers. And they've been doing this in close collaboration with various scientists at the University of Cambridge. And this is why a lab was set up. They worked for a long period of time on single electron devices, so these set devices that we spoke about yesterday, Vivek. And then they've been working on spintronics, and about 15 years ago or 10 years ago, the lab also started working on silicon qubits. And this was about the time where kind of semiconductor-based quantum computing seemed as one of the potentially viable options for quantum computing. And the lab did not work on all aspects of that quantum computing endeavor. They focused on developing single spin readout devices for quantum dots. So for a long period of time, Hitachi was developing these things, and these were things that we were then, selling or giving to industrial or university partners that were doing measurements with quantum dots. And then 2 years ago, the big kind of Hitachi mothership said, we're going to be really, really investing in quantum computing in the future, and we are going to bet on silicon quantum computing as the technology. And there are pros and cons for this, but this is what the big mothership says. And then a lot of money is poured into the kind of research and development part of Hitachi. So they hired a huge amount of researchers in Japan and a small group of people to really be doing academic-like research and communicating with the mothership in Hitachi in Cambridge. So this is when I was hired at the lab. We're a bunch of people there who are researchers and work on different aspects, but about half of us work on this silicon quantum computing endeavor. And I'm the theorist and the kind of amongst the researchers in the laboratory. So we're kind of two people working on theories. It's myself and Norman, but Norman is also the deputy lab manager. So he's a very important person when it comes to the management, but unfortunately does not have so much time to do research anymore. And then we have two PhD students, Joe and Wilfred, absolutely super clever guys. And we've had 3 master students during the past year. And luckily, Chris and Flavio, these two, are going to stay on for a PhD in our group next year. And Kieran is moving to Andreas Wallraff's group at ETH to do superconducting stuff. So it's a really small group, and we have kind of broad interests. So the main kind of interest of the Hitachi mothership is for us to simulate, do numerical modeling of their semiconductor devices, basically. So about 40% of my time and everyone's time goes into doing these simulations and you know, trying to find ways of tweaking the gate fidelities and the readout fidelities little by little. And this is really, you know, work that's highly tied to the experimental groups. Then we've been working on quantum chemistry and the VQE algorithm. So we had a PhD student who just graduated, Jordan Jordanov, who together with me and some other people has the world record for the most gate efficient VQE algorithm for quantum chemistry. We've been doing these projects on quantum metrology and post-selected quantum metrology, which I'm going to talk to you about today. And then we've been writing quantum algorithms for both, you know, quantum machine learning and standard algorithmic tasks. So this is kind of an overview of what we do in this lab. We also kind of collaborate very, very widely. So collaborations is something that both me personally and the lab is really pushing for. Okay, so I'm going to talk about metrology today. I just put up the Wikipedia definition of metrology so that we all are on the same page. So metrology is the scientific study of measurements and estimation. So this is kind of a very broad thing. If anyone checked what the temperature was this morning, either by just going out and feeling or looking at the thermometer, you were doing metrology. You could argue that any physics experiment is measurement or estimation in some way. So metrology is really kind of all of at least experimental science. And here's an outline of the talk. So I'm going to start by kind of laying a mathematical foundation very, very briefly and introduce this concept of Fisher information that perhaps people are familiar. I know at least some people here are very familiar with it. And that will kind of form the basis and the platform for what's going to happen in the talk then. I'm going to introduce what quantum metrology is. It's using quantum phenomena to measure or estimate things. And then I'm going to go to this post-selected metrology thing, which is related to weak values. I'm going to introduce some quasi-probability tools, and then I'm going to use them to see how you can derive bounds in operational tasks in metrology. And after we've done that, if we have time, we can move over to kind of the real new results we've had in the group on multiparameter information distillation in metrology. And then finally, if we have time, I can go through a recent experiment that we've done in collaboration with Ephraim Steinberg's group in Toronto. And yeah, these are the guys. So Professor Crispin Barnes is a professor in the physics department, and Dr. Hugo Lepage is his postdoc that we've been working with. And then Dr. Alex Lasek is a postdoc of Nicole Younger-Halpern's. He was in Cambridge, but now he's with her. And then Flavio is my master student. And then we have a bunch of international collaborators on these projects. So it's a kind of big group effort. Okay. So before I dive into the Fisher information groundwork, I just wanted to give some example of post-selection in everyday life. And the post-selection procedure is just, you know, applying a filter. It's saying, you know, we're going to take some stuff and we're going to throw away some stuff. That is what post-selection is. And it's something we do very often. So if you go out on a very, very bright day, you will struggle to see because your detectors, your eyes will saturate. And in many scenarios, they don't saturate with bad light. It's like all the light that's coming to your eyes are kind of good, informative light that would allow you to perceive the world well. It's just that our eyes can't cope with high intensity. So you could use some sunglasses to lower the intensity and you will see better. And if the sunglasses are just standard sunglasses, you actually reduce the amount of good light, but you still see better just because you avoid the detector saturation of your eyes. And then you can do something a little bit more clever, which is using polarizing sunglasses in scenarios when they help. So for example, if you're driving, the glare of the road or of a sea is usually horizontally polarized. And that glare is not informative if you want to see features of the road or the surroundings. So you can then use polarizing sunglasses that cut out more of the bad light than of the good light. And then you both lower the intensity of the light and increase the good light to bad light ratio. So post-selection is really something that we do. You know, we do it if we are distilling alcohol. Then you start with some low intensity alcohol and you post-select it and you end up with some high intensity alcohol. So this is kind of what we're going for here, but we're going to be doing it with quantum particles, and we're going to try to see what the bounds are for this. I put in some slides on weak value amplification as a start. I don't know, if everyone knows what weak value amplification is, I will skip this.
I'm sure there's at least one person in here who needs a recap.
Okay. So, and given that we have Andrew and Justin here, you know, please feel free to kind of interrupt me when you disagree with something. Lev Weidman saw these slides a few months ago and didn't like them at all. But I'm
not surprised.
Yeah. I've not changed them after his comments because I thought they were pretty okay. Okay, so this is weak value amplification. It's a scenario where we're going to post-select or filter. The idea is this, that there are two particles, phi in and psi in. And these particles are going to get close to each other at some point in space. And there's going to be a Hamiltonian, an interaction Hamiltonian. And we're just going to model this so this like kind of turns on for a short period of time. And the Hamiltonian has some strength, theta, and this strength is weak. So these guys are they're going to come in and then they're going to very weakly interact. And the way they're going to interact is via this Hamiltonian that has a Hermitian observable A on the system psi, and then just a momentum operator P on the system phi. And psi here, I'm not going to say what it is. It's some discrete system. And phi is a Gaussian particle in position space. And this is the setup. The task now is to measure what is the strength of this weak coupling. So what do you do? Well, you could run the experiment a few times where you initialize the psi system as the minimum eigenvalue of A, and then you send through these Gaussian particles many times, and then you have a screen that measures them. And if you do this many times, a Gaussian will appear on your screen, and it will be centered at some value that's proportional to theta times the minimum eigenvalue of the observable A. And we define that to be our 0 point. And then you can run the experiment with some values where you've set this input state to A max, so the maximum eigenvalue of A. And what you'll see is that the momentum operator is the translation operator in position space. So what this is going to do, it's going to shift this Gaussian that originally was centered there to some new value, which is proportional to theta times A max. So if we know what the spectral gap of A is, we can run this experiment many times to make the Gaussians more and more narrow and gain more and more information about what the strength of the weak coupling is, theta. And then the kind of idea of weak value amplification, which is based on this paper from David Albert and Lev Weidman and Yakira Haranov from the 1980s, I think.
88.
88. the idea was that if you brought in a post-selection kind of scenario where you're going to filter this and only send these particles to the screen, given that something happens before, then you could kind of amplify the sensitivity of the screen. So the idea they had was to put in a detector on the system here. And they said, like, only if this detection corresponds to some specific output state am I going to allow this output state to go to the screen. So if this doesn't have this detection outcome, I'm going to block the thing. And what you notice then is that the distance that the peak of the Gaussian moves can be much larger. You will get much less counts because you only send them through given that this succeeds. But if your screen was saturating, you can kind of filter down so that you only send in one particle every time that it's useful to do so. And then what you get is essentially a scenario like this, so a scenario like before, but you've kind of amplified the sensitivity of the screen a lot. And this is something that helps you if you want to estimate what this unknown strength is. So this is kind of the traditional sense in which post-selection or filtering was brought into quantum metrology. Are there any questions or comments at this point? So what we did here was that we went from a large amount of particles reaching the screen with a low concentration of information to a smaller amount with a high concentration of information. And this is what we're going to be trying to do throughout this entire presentation. The difference is that in this talk, I'm gonna try to make things as general as possible. So in weak value amplification, usually you consider an input state and an output state. Most people consider these kind of Gaussian things, but now people sometimes consider both of these to be discrete. The interaction is almost always considered to be weak. So theta is something close to 0. And the interaction has this form of one operator tensored with another operator. Your post-selection happens on just one of the parties, and you keep the other one. So here I'm going to assume a completely general input state. And then the encoding unitary no longer needs to have this Hamiltonian form. It can have loads of kind of parameters. The parameters can be strong, weak, or medium. And the generators of them are not necessarily of this tensor product structure. And then instead of having just a post-selection on the subsystem, I'm just going to say I'm going to do a general P of EM with 2 outcomes. And then I'm going to keep the state given one outcome, and I'm going to throw it away given the other outcome. So this is what we're going for. Yeah. Okay, so I think we're ready to kind of embark on this now. So I said I was going to introduce this concept of Fisher information, so let me do that. So the Fisher information is this mathematical quantity you use to study metrology. And here is my metrological experiment. I call it gamma. And gamma is an experiment where I know absolutely everything except for one unknown thing, which I call theta. So theta could be the temperature or the pressure or a magnetic field somewhere in my experiment. Or it could be, the rotation angle of a qubit rotation in my quantum computer. But it's something I don't know that I wish to learn. So how do I learn this? Well, I send in some input to my experiment. And then I do this many times. And my experiment then will have different outcomes. I call them small m. And these outcomes will happen with some probability p of n. And if your experiment is a clever way of measuring this unknown thing, these probabilities will depend on the underlying parameter theta. So in the best case, the best classical case, you would have a continuum of outcomes M, and there would be kind of a Dirac delta function so that one of them is picked out depending on what the underlying parameter is. But in quantum mechanics, this is not usually the case. And it's not the case in noisy classical mechanics either. So if you run the experiment many times, you will build up the statistics. So you will learn that outcome 2 happened with probability P2, etc. And from the statistics, you can use something like a maximum likelihood estimator to make a guess. So an estimate of what the underlying parameter is. So we call that theta E. And this is how most metrology is done. You run an experiment many times, you collect the measurement data, you run an estimation algorithm that tells you what your best guess is. A natural question to ask is, how good is this guess given a certain experiment? And the answer to the question is, what is the variance? You know? So if you know what the variance is, if the variance of your estimate is very small, then your guess is very good. If the variance is very large, your guess is likely to be bad. Justin.
That seems to be measured precision, not accuracy.
Yeah. So I'm going to be assuming no bias here. If you want to include accuracy, you need to do slightly different things.
Okay, so it's specifically quantifying precision.
Correct. Very, very often, like in most realistic scenarios, you can do clever stuff so that in the limit of many trials of your experiment, you can get rid of kind of accuracy bias. But it's not the most general analysis I'm doing here. But this is an assumption that, yeah. So as I said, if in this no bias scenario, if the variance is small, your guess is likely to be good. If it's large, your guess is likely to be bad. So how can we calculate what the variance is for a general experiment? So as I said, I'm going to assume that we don't have any bias in our estimation technique. So there might be systematic errors in our experiment, but we're going to assume that our estimation technique can deal with these. And we're going to assume that it can deal with it in the limit of an infinite amount of trials. And this is just saying that the expectation value of our guess minus the true value is going to be equal to 0. So if we run the experiment an infinite amount of time, we're going to find the right parameter. And this is something that most estimation techniques satisfy. Not all, but most. So it's a very weak kind of assumption. So if you have this assumption, you can write down the expectation value just in probabilistic language. Looks like this. And nothing stops me from taking the derivative of this thing with respect to the unknown parameter. And then I start evaluating this thing. So I get this formula. And then I use one of my favorite kind of calculus tricks, which is that the derivative of a function is equal to the function times the derivative of the logarithm of the function. So I go from this line to this line. And this looks like some completely strange thing to do, but it will turn out to be a useful thing to have done in a few lines. So I rearrange this thing and I square it. And why do I do that? I do it because I want to take the Cauchy-Schwarz inequality. And what you end up with is this formula here. And does anyone see what this term there is? Yeah, so that's the variance. And what's this thing here? Yeah. So that is the Fisher information. So just by starting from this very, very weak assumption of no bias, we can derive that the variance of our experiment is going to be greater than or equal to 1 over this thing called the Fisher information. And the Fisher information is something you just compute from the probability output of your experiment. If you run the experiment many times, so more than one, so you get an n here. And this thing is called a Cramér-Rao bound. And it says that the variance of your guess is bigger or equal to 1 over the number of trials times this thing called the Fisher information. And in the single parameter scenario, if n is large, this actually always becomes an equality, or it goes towards an equality. So n and the Fisher information directly sets the uncertainty in your experiment. And this is why people in metrology really care about the Fisher information. There are only two ways to make your variance go down. One is to run your experiment more times, and the second one is to redesign your experiment so the Fisher information increases. Okay. So let's see if we can use this to study quantum metrology. Yeah, Daniel.
Sorry, so if you go back to the previous slide, you said that you can enforce, or you can expect your variance to decrease by increasing your Fisher information.
Yeah.
But this inequality is suggesting that a really, really, really good Fisher information doesn't necessarily tell you that you have a good variance.
No, but it becomes an equality if n is large.
Oh, an equality. Oh, okay.
It becomes an equality if n is large. So I'm gonna work in the large n limit today.
Okay.
But yeah, very good point. So I should say it becomes an equality if n is large and you're not doing something stupid. So if n is large, there is something clever you can do to make it an equality. Okay, so quantum metrology. Let's see if we can use any of this in the quantum setting. So the input to your experiment is now going to be a quantum state, and your experiment is going to be a unitary. You could think of it as a general CPTP map, but for keeping things simple today, let's just deal with a unitary. And the unitary has an unknown parameter that gets encoded into the state. Then we do a measurement. And then from these measurements, we would estimate the unknown parameter. To keep the algebra simple, I'm going to assume that our unitary stone's encoded. So e to the I theta a, where a is an Hermitian observable. Everything you'll see today can be generalized to when the unitary doesn't have this form, but things are terrible to kind of go through mathematically then. So the probabilities are just given to us by Born rules. So if we're doing like some POVM with measurement operators EM, then we get these probabilities. And these are the probabilities that we would use to estimate theta. So we could use these probabilities to calculate the Fisher information of this experiment, just by the formula we derived on the previous slide. And then if we wanted to design a good experiment, we would like to maximize this Fisher information. So a question that was asked already in the 90s by Caves and Brownstein was, what is the best possible measurement to do? And what will the Fisher information be if I do the best possible measurement? And they called this the quantum Fisher information. I don't like the name for it because it's really just the normal Fisher information, but optimized over any measurement you can do. So this is what it is. IQ is the quantum Fisher information. And it has this beautifully simple formula. It's the trace of rho theta times lambda squared, where lambda is this less beautiful thing called the symmetric logarithmic derivative. And as you can see, it's kind of implicitly defined by this matrix differential equation. And it's a terrible thing to solve if rho is mixed, but if rho is pure, it's an easy thing to solve. So if rho is pure, the quantum Fisher information takes this form. And you can do a bit of algebra, and then it looks like this. So can someone spot what this is?
Variance of A inside 0.
Yeah. So this is just 4 times the variance of A with respect to size 0. And already here you get something that's kind of reminiscent of a quantum uncertainty relation. because we know that the variance of theta is lower bounded, our estimate of theta is lower bounded by one of the quantum Fisher information, but that's the variance of the generator A with respect to the input state. So what you really get is a kind of Heisenberg-like uncertainty here. And so this is, if someone give you this state, funny. So if someone gave you that state, this is the maximum Fisher information you can get by optimizing the final measurement. And then people will immediately ask, but what if I also optimize the input state? So that's just optimizing a variance. And we know that you optimize a variance by creating an input state that has an equal superposition of minimum and maximum eigenvectors. So if you do that, the Fisher information maximized over measurement and input becomes the spectral gap of A to the power of 2. So for this unitary, if this is the experiment, this is the maximum amount of information we can get out. And if we use mixed states instead, you could only get less because the Fisher information is a convex thing. So this is a bound, and it is really a Heisenberg type bound that the variance of to get the minimum variance of our estimate of theta, we would have to maximize the variance of the generator, and that's the maximum value it can take because it's discrete and bounded. Okay, so this was kind of outlined in details in the early noughties, and then the scenarios are, this is Hugo Lepage's beautiful kind of picture of quantum metrology, where you have your source of quantum particles, you have your unknown thing, and then the information of this thing gets encoded and goes to the detector. And what we're interested in is putting in a filter here, and then seeing what happens to the information content. And why? Well, as I kind of hinted, modern single photon detectors can produce single photons at 1,000 times faster than the best possible single photon detectors can detect them. So if you're using them, you will be actually wasting 999 photons per time bin your detector can detect anyway. So is there a way that we can compress the information from 1,000 photons into one and then carry all that information to the detector? And if there was, that would be good. So let's look at this post-selected metrology business. This is a schematic setup. So it's the same as before. I've just put in a non-demolition measurement here that checks if the state is F or 1 minus F. And if the state corresponds to this outcome, I keep it. And if it's not, I discard it. And F is obviously not a rank 1 projector. So F has higher rank than 1. And the first kind of result we had on this is the following, this theorem, that by putting in a filter here, there is no way that these particles can have more information than these particles if I had done the best input and the best measurement. So filtering cannot increase the information content of these particles above the same cap that we found before in a classically non-negative theory. And I'll tell you what I mean by that in just a few slides. But classically, according to my definition of classically, you cannot break this bound. But quantum mechanics is not a classically non-negative theory. So in quantum mechanics, you can actually break this bound and do clever filtering here that gives you a lot of information. So in order to show you that, I need to introduce these quasi-probability tools that again, Andrew and Justin are really experts on. But they're kind of amazing little mathematical objects that are strange, but really allows you to do quantum mechanics in a different way, and sometimes that different way really helps you in solving problems. So let's just get back. So I want to kind of show this. I want to show that classically there's a cap on how much information you can compress. Quantum mechanically there isn't. So this is what I'm going to go towards. But first I'm going to introduce these quasi-probability distributions. In classical mechanics, if you have a point particle, you can describe it perfectly as a point in phase space. And if you don't know exactly what its position or momentum are, you can still describe it as a joint probability distribution in phase space. And then we know that quantum mechanically, position and momentum do not commute, so you cannot do this quantum mechanically. What you can do is describe your particle in terms of a joint quasi-probability distribution of position and momentum. And the most famous one is the Wigner function. I think paper came out in 1931 or something like that. And Wigner basically defined an object that really looks like a joint probability distribution, but sometimes it goes negative, which classical probabilities don't. And in that negativity, he was able to kind of encapsulate the quantumness of quantum systems with position and momentum. And the Wigner function is a great tool if you have continuous variables or things that map easily to position and momentum, like the kind of real and imaginary part of the electromagnetic field in optics, and many other scenarios. You can discretize the Wigner function as long as you look at kind of mutually unbiased observables, and it's a great tool. Optics people love it. But it has its limits. And it's really limited if you're interested in discrete observables that do not maximally non-commute. So if you have a system and you'd like to describe it as a quasi-probability distribution over two random discrete observables, A and F, with these decompositions, the Wigner function would not be able to help you. And this was the problem that John Kirkwood and Paul Dirac were looking at independently, and just about half a year after Wigner published his Wigner distribution. John Kirkwood was at MIT at the time, and Paul Dirac was in Cambridge. And what they wanted was this quasi-probability distribution where they could describe a state in terms of the underlying observable outcomes of operator A and F. So this is what they were after. They wanted the object to satisfy most, but not all, of Kolmogorov's axioms for probability distributions. So they said, like, if you sum over the thing, it should equal 1. And if you marginalize away over the other observable, they wanted it to give you a probability distribution that matched the Born rule. So they wanted it to be operationally fine with what we knew about quantum mechanics. So what did they do? They wrote down the simplest thing they could think of, which is just to take the individual rank 1 projectors of the observable outcomes and then put in rho in this trace. This is kind of what you would do classically, or what one could do classically. And this is not, this does the job, but it's not a probability distribution. You can take negative or even imaginary values. Okay. A small kind of side note is that colleagues and I have been working kind of on foundational aspects of this, and we find it very interesting. And one thing we've been looking for is, so there are different distributions than this one that satisfy these requirements. And what we're interested in is, are there any minimal conditions we could add such that you nail down that form? So if anyone has suggestions for that, we'd be very happy to kind of receive them.
I would think that would be the simplest possible case, trying to satisfy that. Would there be something more simple?
I mean, the ones we've come up with are certainly less elegant.
Okay.
Yeah. But we don't have an exhaustive proof that this is the simplest thing. It also works if you have more than two observables. If you have like A, B, and F, what you just do is that you extend your thing, and it satisfies the same kind of things. And people might ask, when is this distribution non-classical? And I call it non-classical if it has negative or imaginary components. And if you're interested in finding out when it's non-classical, you can check out this paper by Nicole, Jacob, and me from last year, where we kind of give you really sufficient conditions for when the KD distribution is non-classical. Okay, so why should anyone care about this Kirkwood-Dirac distribution? So one reason is that Dirac tells us to care about it. I was motivated by your comment over dinner yesterday on Dirac's Dirac's work with negative energies and probabilities. So Dirac, there's this quote where Dirac says that negative energies and probabilities should not be considered as nonsense. They are well-defined concepts mathematically, like a negative of money. So this is kind of the schoolboy reason why we should care about them. And the second reason is that they're really useful. So in many scenarios, I have a formula of interest, so some physical formula that I care about. I call it F. And F depends on a bunch of permission observables. Then often I can massage this formula and work on it to get it expressed in terms of a quasi-probability distribution. And then what I can do is that I can find classical and quantum bounds for this thing by saying that what happens if I minimize F with respect to a classical distribution, and what happens when I maximize F with respect to a classical distribution. And these give me the minimum and maximum classical bounds. And I can do these calculations using classical statistics, because under the assumption that things are classical, the KD distribution is just a joint probability distribution. So then all these tricks from classical statistics become available. And people have used the KD distribution, and like, I should have updated this. There are many more papers now, but it's been used, in kind of quantum chaos and scrambling, thermodynamics, metrology, and the foundations of quantum mechanics in really, really different settings. But people use these methods in order to kind of solve fairly hard problems of finding classical and quantum bounds using techniques from classical statistics and the KD distribution.
It looks like most of them are on Mortox. Do you know why?
Sorry?
Most of the papers are on Mortox, right?
The top ones here.
Yeah, they are on out-of-time order.
Yeah. So the out-of-time order correlator is this thing where you have it's just like kind of a Heisenberg type expectation value of 4 observables evolved at different times. And it's something that has a very, very clean form if you write it in terms of a KD distribution. The other reason is that Nicole, Younger, Halpern, and Justin were kind of pioneers in the modern use of the KD distribution, and they were working on Autox. I don't know if you want to add something.
No, that's a good way to put it.
Yeah. In the foundations of quantum mechanics, it's been used quite vigorously, and I don't think it's here, but if you're familiar with the consistent histories approach or interpretation of quantum mechanics, the weights of the different histories are just equal to KD quasi-probabilities. And if the KD corresponding KD distribution is classical, then the consistent histories are, and then the histories are consistent according to the consistent histories interpretation. And the list can be made much longer. Okay. So let's see if I can use this stuff to get some bounds on the post-selected metrology. So this was the setup that we had, right? Initialize a state, unitary, encoded, and do some post-selection. And to keep things simple here, I'm assuming that the unitary is stones encoded by this generator, and that this post-selection here is just like a small part of the identity matrix. So if I would sum over all F here, that would be the identity matrix, but I'm not summing over all F, I'm summing over a part of the identity matrix. I'm just gonna pick out the part of the Hilbert space and keep that. And if you spend a lot of kind of sleepless nights, you will be able to derive what the quantum Fisher information of these states look like. It's this formula here, where P is the probability to pass the post-selection. So this is how it looks. And this is really hard to use kind of linear algebraic calculus in order to optimize and minimize or maximize. But what you can do is introduce this KD distribution here, where the F corresponds to this post-selection operator, and A and A prime are both eigenvectors of the generator A. And then you can get your formula into the following form. So this formula becomes that, and it doesn't look nicer, but anyone who works in classical statistics will immediately see that this is a Bayesian update of an entry in a covariance matrix. And they would be able to optimize that in a split second. So if you do that, and you use you say, I'm going to assume that the quasi-probability distribution is classical, then you can immediately use classical statistics, which tells you that the maximum value of this is again the spectral gap to the power of 2. So in a classically non-negative theory, you can never increase the information content here above some cap by doing post-selection.
So David, let me pause you for a second there. So I view this as summing over entries in a matrix, like if you have like a quadratic form, something like that, sum over A and A prime.
Yeah.
Yeah, so then you can just basically just diagonalize that matrix and look at the eigenvalues to figure out how to bound the quadratic form.
Mm-hmm. Yeah. That's true. I've not thought of it like that, but yeah, that's what you can do. Okay. So this is how we initially used these to show how you could. And then we did the quantum bound, and you can show that if these things can be negative, as they can in quantum mechanics, there is actually no bound on how much information these guys can carry. So quantum mechanically, there's no cap on how much you can distill the information. All of this was for single parameters. So I've just treated this as a single unitary e to the I theta a. If I have another few minutes, I can go through what happens if you have a much more general scenario. Is that okay, or are people kind of drained?
That's fine. I have a quick question first. You said there's no bound, which seems like kind of a big statement.
Yeah.
Is there a way to see from that expression why the bound disappears if you allow Q to become complex or negative?
Not entirely, but I can give you some intuition for why. So what you have here, I said, was a Bayesian update of a quasi-probability distribution conditioned on that we go out there. So you have to take your initial quasi-probability distribution and divide it by the probability of going out there. And that probability distribution is given by the sum of these guys over A and A prime, and F only over the outcomes that come out there. If we want this thing to become really, really large, we would want the denominators to be tiny and the numerators to be finite. Classically, the only way to make the denominator small is by having each and every one of these small, because things can't be negative. Quantum mechanically, if you have a scenario where half of them are negative, half of them are positive, they could cancel to zero, but still be finite there.
So it's the same story. You make your post-selection probability go to zero.
Yeah, exactly.
Right, that's good intuition.
Yeah. The story is kind of circular, repeats itself.
And that makes sense, right? Because you can have something that gets through your post-selection have way more information such that you can collect a bunch of them and get more information than you started with. So there has to be some sort of consistency condition like that.
And I could say as an aside that here we consider these sharp measurements, so sum of projectors. And then for general A, it seemed that even though you could make the information of these guys go to infinity, if you took the information of them times the probability of going through there, you got a half.
Right.
So you seem to be wasting half the information in these trials. But what this brilliant PhD student of Ephraim Steinberg showed was that if you made that a P of VM, similarly to your paper on the entanglement enhanced weak value amplification, if you make that a P of VM, the information of those guys times the probability to going out there can be kept constant. Okay, so let's see if we can really make this on steroids now and go to the multiparameter regime. So, okay, now this thing here is going to have many parameters, and here's this beautiful artistic kind of representation. And we're going to see what we can do. I can say initially that we didn't believe that it would be possible to do this in general if you had many parameters, because in the experiment with Ephraim Steinberg and in our theory on the single parameter estimation, the way we set up F here was directly related to the generator A. But if you have many parameters here, if they don't commute, you have different generators. So first of all, you don't know how your final measurement is going to be, and you don't know how to set F. And maybe you set F to enhance the information about theta 1, but that same F could diminish the information about theta 2. So it seemed just very hard, but we wanted to kind of map out what was happening. So let's go back to the Cramere-Rao bound. If you had just one parameter, you estimated it, was lower bounded by 1 over n times the Fisher information, where the Fisher information was this thing. Now theta becomes a vector of parameters. You can't just talk about the variance of a vector. You have to talk about the covariance matrix, which is this thing here. And then already here, we can see that things get trickier, because how do you know if this is a good covariance matrix? It's a matrix. So usually people want a number that tells you, is this good? So what people then do is that they define a figure of merit, a scalar figure of merit, they call it S, which is the trace of your covariance matrix times a positive semi-definite weights matrix. The most common weight matrix is the identity. If it's the identity, your figure of merit, S, is just the sum of all the variances. But in some experiments, one parameter, maybe the first one, is more important than the later ones. And then you could have a diagonal weight matrix with different weights. But very rarely is the weight matrix not diagonal. There's some scenarios where they are. And then you can use the same kind of analysis that I did up here to show that this scalar quantity is lower bounded by 1 over the number of trials times the trace of your weight matrix multiplying this thing called the Fisher information matrix, the inverse of that. And the Fisher information matrix has entries given by this formula there.
And that doesn't depend on the form of the weight matrix?
The Fisher information matrix does not depend on the form of the weight matrix. The weight matrix comes in just there. It's tedious to show this, but this is kind of, I mean, it's called machine learning now, but statisticians have been using this since the 70s, basically. Just to summarize, so we have some figure of merit S. It's the trace of the covariance matrix times the weight matrix. And we can lower bound that by 1/n times the trace of the Fisher information matrix times the weight matrix. And it just looks kind of impossible. How do you optimize the Fisher information? Before we knew if you just made it big, the variance went down. But now, which entries should you make big or small so that the trace of the inverse of it becomes small? It's just very difficult. It's a very difficult problem. It's an NP-hard problem to do this.
In the simplest case, the diagonals are just the inverse of the original diagonals. Simplest case.
In the simplest case, yeah.
So that's a clear generalization.
But that happens if all the parameters commute. So if there are no covariances. But in general, it's a tedious thing. Let's see what happens. You could ask the same question now in a quantum setting. What happens if I optimize this thing over all possible measurements? So what's the best Fisher information matrix I can get? Well, that's equal to minimizing this thing over all possible measurements. And this is a seriously hard problem. But it's been solved. And the answer is this line here. That the best figure of merit you can get if you do the best measurement, S, is going to be wedged between a quantity times 1 and the same quantity times 2. So what is this quantity? 1/n, the number of trials from before, times the trace over the weight matrix times the quantum Fisher information matrix to the -1. So what is the quantum Fisher information matrix? It's this. It has entries given by this formula there. For those of you who know kind of complex geometry, this is 4 times the real part of the quantum geometric tensor. It's people that know about, Barry curvature and Barry connection are obsessed with this object. So let's see what happens on this slide here. Yeah, so this is the final summary slides of the statistics of multiparameter quantum metrology. Your figure of merit S, which usually is just the sum of the variances, if you do everything right, is going to be between 1 times this thing and 2 times this thing. So if you can make this small, you're definitely going to make your S value small. But again, it seems incredibly difficult to kind of come up with a way of making each and one of the entries in your quantum geometric tensor right. Okay. And we're going to make it even harder by saying that we're going to put the post selection in there. And the first thing we had to calculate, which was a real pain, was an expression for the post-selected quantum geometric tensor. You get what you would kind of intuitively guess, but this is a nasty-looking thing. Again, P is the probability of going through here. So now, the question then is, can you distill information about more than 1 parameters, and how much can you distill? So the only thing you can do at this point is take this formula we've calculated, plug in some F's, and then use this in this relation to the figure of merit S. And we tried a bunch of stuff and nothing worked, and then at some point we had a very, very good guess that just happened to work. So there is a post-selection F you can do that actually amplifies the information about all the parameters at once, which is I didn't believe that it would be possible, but it is. And so I'm just going to show you what that, so how do you choose F? What is the best F to choose? And the best F to choose is only something you can do in an iterative protocol. So you would need something like a Kalman filter or something like this to do it in the lab. And you would have to say that you have 1 million trials of this. You would have to take like the first 100 without the filter to get a rough estimate of what rho theta is. That rough estimate I call rho theta 0. And then the F that you're going to choose is going to be t squared, that's the transmission probability, minus 1 times this initial estimate of what the state is, plus the identity matrix.
So by transmission, this is the post-selection probability.
It's the post-selection probability, yeah. So it seems strange because we need something that depends on the thing we don't know. So the good thing is that we only need a pretty good prior knowledge of what this thing is. We don't need amazing prior knowledge. And you can kind of show that if I define a parameter theta, which is the difference between my guess of theta, of all the values of theta, and the true all the values of theta, then you can use another favorite trick of mine, which is that your guess of what the density matrix is equal to the true density matrix times the imaginary number times a commutator that's linear in this error parameter delta, which seems bad, and it is bad. So like, if you want to guess what the state is, then you're going to be linearly bad with respect to what that parameter is, but you're linearly bad via commutator. And when you plug the commutator into these things here, it vanishes. So when you start calculating the post-selection probability, that's just equal to t squared to second order in delta. You calculate this term, you get some nasty expression, but it's also second order delta. This term also second order delta. This term. So we've gone through like loads of expressions here. And if you combine all of them, you get a really nice result, which is that doing this post-selection uniformly amplifies each entry of the quantum Fisher information by 1 over t squared to second order in delta. And the way we chose F did not depend on which entry of the Fisher information we wanted to amplify or which parameter we wanted to amplify. It just uniformly boosts the entire quantum geometric tensor. So this equation before that we had that looked like an impossible thing to optimize, since we just get this t squared at each entry of the matrix, we can take it outside. And now this t squared is on the top here. So you can just make the transmission probability smaller, and you will squeeze the sum of the variances of all the parameters towards 0. And this is the big result we had last year, and it's kind of counterintuitive that this works, I think. And it's even nicer because if you take the information content of the post-selected states times this post-selection probability, that's equal to exactly the information you had before to delta squared. So it's unbounded and lossless of an unlimited amount of parameters. Or not unlimited, a bounded but large amount of parameters. And then I think I've kind of run over, but is this any good? We worked with Ephraim Steinberg and his amazing team to kind of take this nice picture we had and turn it into something optical, and then Noah, Lupo-Gladstein, and Batuhan built an optical table and did the experiment just for one parameter, where this is the T parameter we had before. And this is the information per photon that reaches the detector. The dark curve here is the one where we chose the best post-selection, so F. And then you could see if you start with T equals 1, we got 1 unit of information per photon. And then by tuning down T, we could amplify the information content by 280 times, something like this. 220 maybe. Yeah. And so it kind of worked. It was something that was useful for these guys. These are some papers we published. And that's it. Thank you.
Any questions from our audience?
I have a small question. The weight matrix you talked, where does that come from? Or...
So this weight matrix here. So your covariance matrix is this thing here. So this tells you what all the variances are of your guesses and what all the covariances are between your various guesses. And then if you are interested in estimating all of these parameters, usually what you want to minimize is the sum of all their variances. And then you set this weight matrix just equal to the identity matrix. If the first entry is more important than all the others, you have a weight matrix where the first entry is bigger than the others. It's almost always a diagonal thing. Sometimes the covariances matter, and you want to limit covariances or increase covariances, but usually you don't. It has to be a positive semi-definite matrix, though, for this to work.
Other questions locally?
Can you go to your selection of this perfect or optimal choice of F for the multiparameter case? Yes, so the identity plus t squared minus 1 theta phi. So if I think about t squared as my successful post-selection probability, right? Basically, I'm taking that post-selection probability times my state, and I'm subtracting state, and I'm adding the identity. And I guess, so usually you would want your overlap between F and rho to be 0 or close to 0 to get the amplification. So is that the same kind of picture you have here?
Yeah. So if, let's assume just for the sake of argument that we had a perfect guess of what rho theta was. If we had a perfect guess, this type of F, it takes the state that comes in and it looks at it, and it says, if this state is rho theta, I'm going to transmit it, but only with probability t squared. If it's anything else, I'm going to transmit it. So if you think of this in terms of kind of a diffraction thing, it's turning your whole state into a very, very small diffraction thing, and then it's zooming in on a dark spot. So you're kind of doing interferometry at the dark spot of that pattern. And it's exactly what you said, that you're trying to throw away as much as you can of the state that you expect to actually be there.
Yes, this is like subtracting a background to get only the deviations.
Yes.
So if I just multiplied by rho and took the trace, for example, I would get something like, would I get something close to 0?
T squared plus delta to the power of 2.
Yeah.
So if we take the, let's see, yeah. Here, so we just multiply by rho, and then you get t squared plus something.
I see. Let me just look at the steps of your derivation for a second there.
I should tell you what C is. C is this commutator between the
Yeah.
true state and something linear in
So
there.
you have to add in this other little thing.
But if you have a perfect guess, C is 0.
So you're adding this IC commutators because you don't know the rho theta.
Exactly, yeah. So I say I only know to first order, but it doesn't matter because the effect is only to second order.
Nice.
And then in some scenarios, so when I was at MIT, I talked a lot about with Seth, who's doing kind of quantum imaging and stuff like this. And then, so one idea they had, nobody has actually done that, was to say that you have a quantum state that encodes an image. And then you want to find any errors in this. So then you could assume that you know this perfectly, and you set this up with the state that you know perfectly, that this is the state you want. And then you would massively amplify any deviations from that image that you're interested in. Daniel?
So if I understand correctly, this post-selection, this app, what it's doing is it's almost like taking the negative of an image, right? So you use the states that have what you want to measure, what you would predict, are going to be more dark. So
yeah.
So then turning the transmission probability to be very tiny is kind of like tuning up the contrast of your image, essentially, because you're going to be picking out more of what you would expect to see. Is that a good?
I'm going to pass this question to the photography expert in the room. And,
Yeah, so I think that's the right intuition. So if you have an image that has some deviations that give you all the information, you subtract the reference image.
Right.
Then all you'll have left are the deviations, and so you'll get the maximum information from anything that's not black in the image.
Right. So in this sense, this filter is telling us how much does what we measured deviate from what we expected. Okay. So
It's a little more complicated though, because this only works mechanically.
That thing is used in similar, to find, like, to the imaging, Google and they use that thing to, like, kind of detect the image, right? Because they do filtering, they don't do everything.
Yeah, so classically, this is kind of what you'd want to do anyway, but the difference here is now this is a quantum filter that's getting more compression out of it than you can get just by a dark subtraction classically.
yeah.
Dark subtraction isolates where the information is, but doesn't boost it. This is actually boosting it while isolating it.
Just because it's looking at
Have you thought at all about the estimators? So you prove boost of below all your information, Fisher information by 1/p. What about the estimators though?
Yeah. So we can use these bounds here. So this thing here is actually the estimators. So we will boost all of these estimators similarly. So whilst the Fisher information is boosted by 1/t², all the estimator, the combination of all the estimators gets shrunk.
I thought that was just your global variance.
You mean the individual estimators?
Yes, so if we remember we started, theta 1, theta 2, theta 3. How do I then estimate theta 1, theta 2, theta 3 from the data?
Yeah. So they're rigid techniques for how to do that, and we're not telling you how to do that. We've not looked at that. We're just saying that if you use unbiased estimators in the optimal way, the combination of them you'll be able to do it well. But
So usually you do like maximum likelihood, and you find maximum likelihood estimation. And so is that what you're then appealing to?
Mm-hmm.
Or, okay.
Do you happen to know what Ephraim's lab did for estimation strategy in your experiment?
yes. So I'm trying. Let's see. It might even be here. So let's see. We initialized some horizontal single photons heralded. They went into this halfway plate, which was tilted by alpha, and then we related alpha to some theta. So this was the unitary. It's a polarization rotation.
So you're finding effectively just the unknown tilt of this way.
Yeah.
Okay.
And then this, so we knew that the state was initially in 1. This is, if we assume that theta is weak, which they did, then this was the optimal F that they used.
But I think Justin's asking, eventually
okay.
you get clicks on your detectors, right? So how do you combine the clicks in a way to estimate what theta is?
Oh, okay. So not okay. Yeah, I don't. Like they use kind of sophisticated things.
Probably maximum likelihood.
Yeah, but yeah, so I'm not sure if there was any Bayesian stuff going in there.
Well, that's usually how you derive what the estimator is. And so then it's some function of the number of clicks you get in a certain amount of time. So you put that into your, it could be a nonlinear estimator, and that would be your max-like estimate of, and that should be the optimal for unbiased estimation.
Right. So yeah, I'm not sure what they used.
Interesting. This is a single parameter case.
Yeah.
This is a single parameter case. So we've not done, if you guys and John would be happy to do a multi-parameter case, that would be fun.
That sounds interesting. Showing exactly what the multi-parameter case is doing.
And so I said I just kind of guessed what this F should be. The guess was just based on this post-selection that the very clever student Noah was using. So I just thought, how would that look in the multi-parameter case? And that just worked.
Yeah, the intuition makes sense.
Yeah.
Okay, great.
Anything from our remote attendees? Guess not. I'll thank David again.